So let's start with number 7 here. Try problem 7.
Solution of unknown non-volatile non-electrolyte was prepared by dissolving 0.250 grams and 40 grams of CCl4. The normal boiling point of the resultant solution is increased by 0.257 degrees Celsius. Calculate the molar mass of the solution. Kb is equal to 5.02 degrees C. Okay, well, we know that it's delta Tb is equal to Kb times molal times I, where I is equal to 1. And we have the grams, and we also want to figure out the mole mass, which is grams of solute over moles of solute. And since we know that the increase is 0.357 degrees C per 1 mole, that is equal to Kb, which is 5.02 degrees C per 1 mole, times m times I. So then we just divide these two. It's 0.357 divided by 5.02. And that is equal to the molality, which is equal to 0.071. And since this is 0.071 moles of solute over 1 kilogram of carbon tetrachloride, then we can multiply this by 0.040 grams of carbon tetrachloride. Oops, 0.07. And that is equal to 0.003 moles of solute. Let me just take the, what is it, 0.250 grams of solute, divide that by 0.003 moles of solute. And I get 83.3 as the molar mass, grams of solute over moles of solute.
Okay, what was that answer again?
83.3.
And the units were?
Grams of solute per mole of solute.
So let's review that process. Sounded like you started by writing down the units for what they were asking you. We saw last time that that was a good approach. Then you used this formula. How did you know that I was 1?
Because it says there's a non-volatile, non-electrolyte is dissolved in the solvent.
So what is the clue word that tells us that I is 1?
Non-electrolyte.
Non-electrolyte. I don't think you and I really talked about that term electrolyte last time, but maybe you've seen that already in class. And electrolyte is a solute that breaks up into ions. So if it's non-electrolyte, that means it doesn't break up into ions. So that's what we saw last time would give us an I of 1. And then when you got the molality, you did a unit conversion like we did last time. What are the units that you had written here? 0.040 what?
Kilograms.
Right, this should be kilograms, not grams, because we had to do a unit conversion, so it would be consistent with these units. And then what did you get as the number of moles of solute?
I got 0.003.
Does that look like this?
Yeah.
Now, I don't think I got that on my calculator. Try that calculation again on your calculator. One of us must be making a mistake.
When I take delta TB and I divide it by KB, I got the first number that I had was 0.07.
You're right.
And then when I take that number and I multiply it by 0.04, I got my same original number, 0.03. And then when I take 0.240 and I divide it by that number, I get 87.8.
So this is the calculation you're doing? Or not?
Yeah.
And what did you say you got?
87.8.
I'm getting 83 there. Why am I getting this wrong? 0.07 times 0.04 is 0.003. And then you did 0.25 divided by 0.003?
Yeah. Well, the thing is I keep my significant figures, so I didn't round it up to 0.003, and that's what it came out to.
Right.
7.8.
That's probably better, so 0.028. That's too much rounding. And what did you have on the top here? 0.25. Why is this not coming out right for me? 0.357 divided by 5.02. 0.0071. 0.0071 times 0.04. That would be like this. And then 0.25 divided by 0.00284. So now I'm getting that as 88. So it looks like there's just some rounding error issues. So what was the answer you got?
88.
Okay, good. So I have the answer to this. They got 87.9, so that's pretty much the same as we're getting. Yeah, so we don't want to round off too much here. That can lead to some mistakes. So it sounds like what you're saying is that you had the right answer originally?
Yeah.
Yeah, you had the right answer and I just made a mistake. I led you down the wrong path. Okay, good. You did it right and I did it wrong. So this is the type of problem that we ended up last time with. And it looks like you're remembering better than me how to do it. So that's good. Okay, good. So also from last time, oops. Let's review this. What's the symbol for molarity?
Let's say capital M.
And what are the SI units for molarity?
Grams. I'm sorry. It's moles of solute divided by liters of the solution.
So what's the symbol for molality?
It's lowercase m.
And the units?
Moles of solute divided by 5 kilos of solvent.
Good. So we went over that last time. That's good that you remember the differences between molarity and molality. Here we have solution, and here we have solvent. Here we have liters, and here we have kilograms. I think last time we talked about the difference between the solute, the solvent, and the solution. We've also been talking about molar mass. So sometimes molar mass is abbreviated as capital M, although you'd have to make sure you didn't confuse that with molarity. So what are the units for molar mass?
Grams of solute over moles of solute.
Right. Now, actually, this could apply to anything, not just to a solute. It could be grams of salt. The molar mass of the solute is grams of solute over moles of solute. But the molar mass of the solvent is grams of solvent over moles of solvent. Maybe we could call it grams of X over moles of X, just to show that the same substance is on the top and the bottom, unlike these two. So that's units that we were using on the previous problems. Now, another term I think you might see on the test is molecular weight. I don't know if you happen to remember what the units are for molecular weight.
Atomic mass units.
That's right. Good. We didn't talk about that before, but that's right. Atomic mass units. So if the molecular weight of a substance is 18 AMU, how would you interpret that in words? Do you know what this means? What does that tell you if the molecular weight is 18 AMU?
It's 18 atomic mass units.
Who's it?
The element, or actually not the element, but the substance, the molecule.
How much of the molecule would have a mass of 18 AMU?
The whole thing.
Okay. All right. Yeah. Now, the one thing I wanted to make sure that we're clear about here is when we're looking at, when we say AMU, we mean one molecule or one formula unit. So here we would say one molecule or formula unit has a mass of 18 AMU. Whereas here we're talking about the mass of a mole. That's the distinction between molar mass and molecular weight. The molecular weight gives you the mass of a molecule, whereas the molar mass gives you the mass of a mole. However, something that's convenient is that the number mole, Avogadro's number, has been picked to make it really easy to go back and forth between molar mass and molecular weight. For example, if so 18 AMU, if something has a molecular weight of 18 AMU, what would be its molar mass? And it turns out it would be 18 grams per mole. That is, the numerical value of the molar mass is always the same as the numerical value of the molecular weight. Numerically, molar mass and molecular weight are always the same. That's just because the Avogadro's number for a mole was picked to be a very convenient number that makes these numerically equal. This is water, by the way, right? You can see from the periodic table, oxygen is 16 and hydrogen is 2. So the molecular weight would be 18 AMU, and the molar mass would also be 18, but 18 grams per mole. So if you have one molecule of water, what's its mass? If you have
18 grams per mole.
Now, that didn't quite answer the question I asked you. What I asked was if you have a single molecule. If you have a single molecule of water, what would you say its mass is?
Oh, 18 AMUs.
That's right. How about if you have 1 mole of water? What would its mass be?
18 grams per mole.
Yeah, or just 18 grams, since I said 1 mole. Okay, good. So is the AMU a small unit or an ordinary sized unit?
It's an ordinary sized unit.
Actually, if you think about what it measures, AMU must be a tiny unit. Because remember, AMU is used for measuring the mass of individual molecules. I mean, how much is the mass of an actual water molecule? It's tiny, 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 right? Since a molecule is tiny, the mass of any individual molecule would be tiny. And since we measure that in AMUs, that must be a tiny, tiny unit. So AMUs are a very small unit because they're used for measuring very small things, molecules. How about grams? Are grams a small unit or an ordinary sized unit?
Grams are ordinary size unit.
Yeah, because they're used for measuring an ordinary amount of substance in moles. So grams are an ordinary sized unit. And how about AMUs? Are they ordinary sized or very small?
Very small.
That's right. So that's the distinction between these. Technically, molecular weight should really be called molecular mass. This isn't really the weight, it's the mass, but this is the common term, molecular weight. So going back up to this problem I asked you here, oops, well actually I guess the problem was, well, up here the problem I think was asking you for the molar mass, right? This problem was asking us for the molar mass, and this was the answer we got. Suppose that we got 88 grams per mole. Suppose it had been asking you for the molecular weight. What's the molecular weight of this substance?
The molecular weight would be 88 AMUs.
That's right. So we didn't talk last time about that, but that's something else you might see on the test. Instead of asking you for the molar mass, they might ask you for the molecular weight. And I guess the best way to solve that is first find the molar mass still. It's still best to find the molar mass because grams and moles are the types of units that the rest of the problem is about. And then step 2, just convert that into the molecular weight. So even if they ask you for the molecular weight on these problems, it's best not to think about that directly. Still get the molar mass first, and then it's easy to convert because the numerical values are the same. So that's something we didn't quite have time to talk about last time. All right, so that would give us these. Okay, so here's a practical application. In winter, sometimes the city will put salt on the roads. What good is that?
Well,
So when it snows, when there's a bunch of snow or ice on the roads, or they're worried about there being snow or ice on the roads, they put salt on the roads to try to prevent the ice from forming. Why would salt on the roads prevent ice from forming?
well, depending on what kind of a salt it is, it's in the presence of water, it's probably gonna be, like warm or hot. So that way the snow's gonna melt.
Okay, so it sounds like you're saying that the salt will be warm and that will melt the ice. I suppose that's possible, but that's not the major effect here. After all, the salt might just be at the same temperature as everything else. Since the truck is carrying around the salt on the outside, the salt's likely to be pretty close in temperature to everything else. So it's not that the salt is warm. What we want to do is use the colligative properties that we've talked about. So for example, suppose that there is a bunch of water on the roads. If during the winter there could be a bunch of cold water from snow on the roads. If you put salt in the water, what's going to happen to the water's freezing point?
It's going to increase the boiling point.
You said it was going to increase the boiling point? I think that's right.
Yeah.
What's going to happen to the freezing point of the water?
Oh, the freezing point is going to decrease.
Because the term, remember, is freezing point depression. So if the freezing point decreases, does that mean that the water is more or less likely to freeze?
It's going to be less likely to freeze.
Because it means it'll have to be colder to freeze it.
Mm-hmm.
Instead of freezing at 0 degrees Celsius, the temperature might have to fall to, I don't know, -3 degrees Celsius or -5 degrees Celsius. So if it's less likely to freeze, are you going to have more or less ice on the roads?
Less ice.
Right. So that's mission accomplished. the city doesn't mind if there's water on the roads, but they want to avoid ice because ice is slippery and causes accidents. So this is something I think that cities actually sometimes do to try to reduce the amount of ice on the road. So they're using the colligative property of freezing point depression. So the reason why the roads are salted is to achieve freezing point depression. It's not because the salt is warmer, but because it changes the freezing point. So that's an important application that could even come up on the test. I guess another application is in your car, you put a antifreeze. I guess antifreeze is another liquid. You put the antifreeze liquid in the water in the car's radiator. What do you think is the purpose of that? Why do we put this solute in the water in the radiator?
So that the freezing point decreases, so that the ice or the water is less likely to freeze.
Right. So in order for the water in the radiator to actually serve its function, it has to be liquid. It's not supposed to freeze, but if it's really cold outside, that water might freeze. So the antifreeze prevents that. Most of the problems that we've been doing, we've been using solid solutes, I think. But you can also put in a liquid solute, and that would also decrease the freezing point here. That makes it less likely to freeze. Also, I guess, does the antifreeze, if it's really hot outside, would the antifreeze make the water more or less likely to boil? What does it do to the boiling point?
It's going to make it less likely to boil.
What does the antifreeze do to the boiling point?
It'll increase the boiling point.
That's right. Does that make it easier or harder for the water to boil?
Makes it harder for the water to boil.
Because the way to boil something is by raising the temperature, and now we have to raise the temperature higher. So that's good. That's good as well. I don't think that was your first answer. It sounded like at first you were saying it was making it easier to boil. Maybe because this arrow is opposite of this arrow. But the way you boil something is by having a high temperature. So if the boiling point is higher, that makes it harder to boil. Well, that's good too. I think that's another function of antifreeze. When the weather is really hot, you don't want the water to vaporize in the radiator. I guess it's not just that we're changing the boiling point. You wouldn't really expect the water to boil. It's not going to be that hot that the water is going to boil. But in general, this would help to prevent the water, I suppose, from evaporating. So the point is that if you put the antifreeze in water, that makes it less likely to freeze out, and it also makes it less likely to evaporate when the temperature is high. So those are two real-life applications, and it wouldn't be too hard to make test questions about those. Okay, so let's see. So now let's talk about the idea of mole fraction. So let's say we have a solute in a solvent. What's the mole fraction? Of the solvent. So for example, suppose we have 2 moles of solute in 18 moles of solvent. Let's actually calculate mole fraction of the solute. Are you familiar with this term? How do you think you would calculate the mole fraction of the solute here?
Well, it's just 18 moles of solvent divided by 20 moles total, and that gives you 0.9.
Good. Except notice here we want to know what fraction consists of solute.
Oh, solute. I thought you.
I actually, sorry,
I
I changed the question.
Solvent. Oh. It would be 2 moles of solute divided by 20 moles total, which is 0.2.
So it would be 2 over 20, or 0.2. How would you interpret that? That means 20% of the moles in the solution consist of solute. All right, and what calculation would you do to figure this out?
18 divided by 20.
Yeah, as you were saying before.
So that's equal to 0.9.
So that would mean 90% of the moles consist of the solvent. Okay, so this is a new concept that we need. This is another way of measuring concentration. Do you happen to know what the symbol is for mole fraction?
M little f.
M little f. That would be a very logical symbol. So that's a good try. It turns out though, but that might be confused with molarity or molality or mass. So instead, they just use capital X. So that's our new symbol. Capital X is our symbol for mole fraction. Here this would be X sub solute, and this would be X sub solvent.
And you said 0.9 means that 90% of the solvent, or of the solvent contains the solute?
No, that's a good question. Let's go back to this. This means 90% of the moles in the solution are from the moles of solvent. So this means of all the moles in the solution, 90% are moles of solvent. And this means that of all the moles in the solution, 20% are moles of solute. Of course, 100% are moles of solution, because as we talked about last time, the solution is the whole. Does that make sense?
Mm-hmm.
So if X solute is high, does that mean we have that the solute is concentrated or dilute?
It's concentrated.
A concentrated solution usually means lots of solute. Does that mean that the solute is crowded or not crowded?
It's crowded.
Now, if X solute is high, what do you think that would tell you about X solvent? Would the mole fraction of the solvent be high or low?
It would be low.
So, if you have a very concentrated solution, X solvent is low. So notice that you don't want to confuse the mole fraction of the solute and the mole fraction of the solvent. They go in opposite directions. If we have a dilute solution where the solute is dilute, what would that tell you about X solvent?
It's not crowded.
Would X solvent be high or low?
It would be low.
Let's think about that again. I guess we have to do that more step by step. If it's dilute, would X solute be high or low?
Oh, would X solute? X solute would be low.
But the original question I asked you was, if it was dilute, would X solvent be high or low? So if the solution is dilute, would X solvent be high or low?
X solvent would be high.
Right. I thought it sounded like your original answer was that X solvent would be low. So you might have been confusing that with the mole fraction for the solute. So as I said, this could be confusing because these move in opposite directions. Basically, if the solute, here the solute is not very crowded, that means there's more crowding for the solvent. All right. So it's important to try to distinguish between these. Let's say that we had a open container of water. Let's say we take this open container of water and we put it in a larger closed container. Maybe a larger closed container that has a vacuum inside of it. It doesn't have to be a vacuum, I guess, but a larger enclosed container that has no water vapor in it. What would happen here? Well, this water would start to evaporate. As the water evaporates, there would be less and less liquid water. And there would be more and more water in the air. So these are water vapor molecules. Water vapor molecules. So we'd have more and more water vapor molecules in the air. But as more and more water vapor goes into the air, some of this water vapor is going to start recondensing into the liquid. In this picture, we're only going to have movement in this direction, but in this picture, we'll have movement in both directions. And eventually, these two movements will just cancel each other out and will be in equilibrium. So the liquid doesn't have to evaporate forever. If the container is closed, the liquid won't evaporate forever. It'll eventually reach an equilibrium where it's evaporating at the same rate that it's condensing. And then we could measure what is the pressure of the water vapor. And there's a term for that. That's called vapor pressure. And this is a little bit of a misleading term because this is not just the pressure of the vapor, it's what the pressure of the vapor will be at equilibrium. It probably would be better to call this the equilibrium vapor pressure. But usually it's just called vapor pressure, and we're expected to know that they mean the pressure of what the vapor would be at equilibrium, when the vapor is condensing at the same rate that the liquid is evaporating. So this concept would really, you'd only reach equilibrium if the container is closed, because if the container was not closed, the water vapor would keep escaping, and there wouldn't be very much of it that was ever recondensing. If the container was open, I suppose that the liquid would evaporate completely, just like if you have a puddle on the street, the puddle eventually evaporates completely. So to think about this, we need to think about a container that's closed. Okay, so that's our concept of vapor pressure. So I guess we have to review the idea of pressure. Usually a good symbol for pressure is P. Maybe we'll use capital P here. Do you remember any units for pressure?
I believe torr or millimeters of mercury.
Good. If something has a pressure of 30 torr stands for torricelli. So if it has a pressure of 30 torricelli, do you know what would be the pressure in millimeters of mercury?
I believe it would be the same, 30 millimeters of mercury.
The same, that's right. So torricelli and millimeters of mercury are the same name. Are there different names for the same unit? So these are different names for the same unit, so it's easy to convert between these. These are just different names for the same unit. There's one other common unit for pressure that's used in a chemistry class. Can you remember any other units for?
The Pascal.
Yes, there's pascals. That's the SI unit, But actually that's not used very much in a chemistry class. That's more for a physics class. Your class might not be using pascals. I didn't see that in those handouts. The other unit that's common in a chemistry class is atmospheres. For example, do you know what's the normal pressure, say, in your room right now?
I don't know.
It's actually 1 atmosphere. Approximately 1 atmosphere. Atmospheres are a unit that are chosen so that so it makes it easy to talk about actual atmospheric pressure. So normal atmospheric pressure is 1 atmosphere. That's why it's called atmospheres. Do you know what's the conversion between atmospheres and Torricelli? If you have your textbook with you, you might look that up.
I don't.
Let's see. So our conversion here is 1 atmosphere equals 760 Torricelli, or 760 millimeters of mercury. You might be expected to have this conversion memorized. Okay, so these are the units that we might need. This is for any type of pressure, so we can apply it to a vapor pressure. Notice that vapor pressure is not measuring the total pressure of the atmosphere. It's just measuring the pressure of the vapor molecules from the liquid. So for example, if this was water, this would just be the pressure from the water vapor. It wouldn't be the pressure from the oxygen or the nitrogen in the atmosphere. This is the partial pressure just of the water vapor. This can apply to any liquid. I've been talking about water, but it could be any liquid. All right. So if the vapor pressure is high, do you think that that indicates that the liquid is eager or not eager to vaporize?
Could you say that again?
If the vapor pressure is high, do you think that means that the liquid is eager or not eager to vaporize?
It's not eager.
Why would you say that?
Not quite sure.
Well, let's put it this way. Remember, the vapor pressure is what the pressure of the vapor will be at equilibrium. Suppose that you're going to have lots of vapor at equilibrium. If there's going to be lots of vapor at equilibrium, would the vapor pressure be high or low?
Oh, it'd be high, so there wouldn't be, like, in a closed container, there wouldn't be any room for any more water to evaporate.
Yeah, now that's not quite the right way to think about it. Remember that the vapor pressure is what the pressure of the vapor will be at equilibrium. So once you reach vapor pressure, there's never going to be any more net evaporation. Once you reach a pressure that's equal to vapor pressure, there's never going to be any more evaporation because you're already at equilibrium. The question is the pressure at equilibrium high or low? When you get to equilibrium, was the vapor pressure high or low? So for example, if we have high vapor pressure, then at equilibrium there would be lots of water molecules around. On the other hand, if we have if we have low vapor pressure, then the liquid is not going to fall that much in height, and then there's only going to be a few water molecules at equilibrium. Well, the way we should interpret this is, in this case, clearly the liquid was not eager to vaporize. In this case, the liquid was not eager to vaporize because it ended up with only a small number of vapor molecules at equilibrium. Whereas in this case, the liquid was eager to vaporize because we ended up with a high number. So if the vapor pressure is high, that means that it is eager to vaporize. Now, once it reaches equilibrium, it won't be vaporizing anymore. But the point is that it's eager to vaporize, so there will be a lot of gas molecules at equilibrium. So vapor pressure is a measure of how eager the liquid is to vaporize before it reaches equilibrium. When the vapor pressure is high, that means we're expecting to end up with lots of vapor molecules, so it must be eager to vaporize. If the vapor pressure is low, does that mean that the substance is eager or not eager to vaporize?
It's not eager.
If we're going to personify it. I guess this is a little bit of a subtle or confusing concept because the point is, what we mean is the vapor pressure tells you how eager something is to vaporize before it reaches equilibrium. Once it reaches equilibrium, it's never going to vaporize anymore on net. But this tells us how eager it is to vaporize before. Okay, so that's the common sense of this concept that is important. Remember, if we say the vapor pressure is high, that doesn't mean there's already a lot of vapor. That just means that there will be a lot of vapor when we reach equilibrium. Remember that a better name for vapor pressure would be equilibrium vapor pressure. Okay, that's actually a little bit of a subtle concept, but hopefully that'll be good enough. So, let's see. Now remember, when we add solutes to the solvent, we discussed last time, does that make it easier or harder for it to leave the liquid phase?
It makes it harder to leave the liquid phase.
Harder to leave the liquid phase. Whoops. That's why the boiling point increases. It's harder to boil, and the freezing point depresses. It's harder to freeze. So if you add solute to the solvent, would that make it more or less eager to vaporize?
It's going to make it less eager to vaporize.
So would you expect the vapor pressure to increase or decrease?
Decrease.
Could you say that again?
Decrease.
Good. So what happens when you add a solute to a solvent? Vapor pressure increasing or vapor pressure lowering?
Vapor pressure lowers.
That's right. So that's our next colligative property. Vapor pressure lowering. We've talked about boiling point elevation and freezing point depression. So the next colligative property is vapor pressure lowering. And we can kind of predict that because all of the properties have said that it's harder to leave the liquid phase. If it's harder to leave the liquid phase, you would expect that there's going to be less vapor at equilibrium. That means that the vapor pressure has lowered. So that's our next property here. Okay, good. Vapor pressure lowering. We can actually give a more concrete explanation for that. So when the liquid vaporizes, the part that is vaporizing normally is just the liquid at the surface. Normally it's just the liquid at the surface that is going to vaporize unless it's boiling, which we're not talking about right now. But normal evaporation, it's only the liquid at the surface that's going to vaporize. So what happens when you stick in a bunch of solute particles? Notice that when there's solute particles, Some of the positions at the surface aren't occupied by solvent anymore. They're occupied by these solute particles. So now that we've added the solute, is there more or less solvent at the surface? Now that we've added the solute, is there more or less solvent at the surface?
There is more solvent at the surface.
That actually wasn't what I was going for there. So if there was no solute, it would be 100% solvent at the surface, right? Here's a case with no solute. If there's no solute, then everything at the surface is solvent. But now when there is a solute, some of the particles at the surface will be solvent, and some of the particles at the surface will be solute. So when we add solute, if we add solute, does that mean there's more or less solvent particles at the surface? Is there going to be...
Oh, there's less solvent.
Yeah, there's going to be less solvent particles at the surface. Does that mean that the solvent is going to be more or less likely to vaporize?
Less likely to vaporize.
Less likely because it can only vaporize when it's at the surface. It can only vaporize when it's at the surface, and some of those positions are blocked. So basically, remember that in order to vaporize, the solute has to escape into the atmosphere, and you can just think that the solute is getting in the way. It's harder for the solvent to escape into the atmosphere because the solute particles are getting in the way. That's a pretty straightforward explanation now for why we have vapor pressure lowering, for why the vapor pressure would decrease. And this is actually then, this really explains why there's also boiling point elevation. If the vapor pressure is lower and the substance is less eager to vaporize, it should make sense that it's also going to be less eager to boil. So the boiling point is going to increase. Technically, the boiling point is where the vapor pressure equals the atmospheric pressure. So if the vapor pressure is lower, you need a higher temperature to reach that boiling point. You could also use that to explain freezing point depression, but that's a little bit more subtle, so we don't need to get into that. But anyway, it's pretty clear to see why the solute vapor lowers the vapor pressure. It just gets in the way and makes it more difficult for the liquid to evaporate, so that we'll end up with less vapor at equilibrium. All right. So let's say we increase the mole fraction of solute. What do you think is going to happen to the vapor pressure of the solvent?
Then the vapor pressure of the solvent will decrease.
That's right, because remember, the solute particles are getting in the way and making it harder for the solvent to evaporate. So this is what we would call the vapor pressure. I'll use this symbol for the vapor pressure. Let's say we increase the mole fraction of the solvent. What's going to happen to the vapor pressure of the solvent?
It's going to increase.
This is a little more subtle, but remember, this means there's actually less solute to get in the way. This would mean there's less solute to get in the way. The solution is less concentrated, so more of the solvent can vaporize. Let's try to get an equation here for the vapor pressure of the solvent. So should we put X solvent on the top or the bottom of this fraction in order to represent this relationship? Should we put the mole fraction of the solvent or the top or the bottom here?
On the top.
That's right, because we want them to move in the same direction. Actually, it turns out that for this fraction we don't need a denominator. And then the other thing that the vapor pressure of the solvent depends on is just this. This symbol is the vapor pressure of pure solvent with no solute. This symbol stands for the vapor pressure of the pure solvent if there was no solute in it. Let's say we have lots of solute. What would that do to the mole fraction of the solvent? If there's lots of solute, what would that do to the mole fraction of the solvent?
It's going to decrease the mole fraction of the solvent.
That's right, because now a small fraction is going to be solvent, a greater fraction will be solute. What does that do to the vapor pressure of the solvent?
It decreases it.
Now there's two ways to see that. First of all, you can see that from our formula. The formula says that if X solvent is low, P solvent is low. But remember, that's also our common sense. We know that there's lots of solute that's going to get in the way and make it harder for the solvent to evaporate. So the point is that the formula here is matching our common sense for what should happen to vapor pressure. Let's say that there's only a little solute. What happens to the mole fraction of the solvent?
It's going to increase and also increase the vapor pressure.
And again, notice that that matches the equation and it also matches common sense. In the equation, we can see this term bigger makes this term bigger. But if there's only a little solute, then almost all the solvent is, there's almost all the particles at the surface are solvent, and it's easier for it to evaporate. Let's say there was no solute. If there was no solute, what would be the mole fraction of the solvent? We haven't quite talked about this, but if there's no solute, what's the mole fraction of the solvent?
Well, I don't think there would even be a mole fraction.
It might be a little weird to calculate it, but we can still calculate it. If there's no solute, what percent of the moles come from solvent?
100%.
100%. So what would be the fractional value? 1. 1 equals 100%. And then what would happen in this formula? According to this formula, then, in that case, what would be the vapor pressure of the solvent?
100%, or yeah, it'll increase.
So think about that a little bit more. What exactly would be the vapor pressure of the solvent if X was 1? What would happen in that equation?
Well, if X was 1, then it would just be the vapor pressure of the pure solvent.
Which is just obvious, right? So then you would get P solvent equals P0 solvent. But what does P0 stand for?
It's the vapor pressure of a pure solvent without no solute.
And that I'm just showing, so we're just showing that the equation makes sense because this is the pure solvent with no solute. So we're showing that this equation would still give you the right answer even if there was no solute at all. So by the way, what's the biggest that X could ever be? What's the biggest that X can be?
1.
1. You can't have more than 100%. And the smallest it could be, the lower bound is 0. You wouldn't ever be exactly 0 for the solvent, but it's between 0 and 1. Okay, so this equation, that's the intuition for why this equation makes sense. Notice that you have to be careful here in this equation. Notice none of these are directly about the solute. None of these terms are directly about the solute, but you need to use information about the solute to work this out. All right. One second. All right, so try working this out. Try working this out on paper and tell me what you're writing down for your steps.
Well, let's see. We want to figure out the vapor pressure. So we're trying to solve for P. And we know that P, the solvent, is equal to X solvent times P0 of solvent. So vapor pressure of pure water is equal to 23.8 millimeters of mercury. And times that by X solvent. So now we have to take 90 grams of glucose and convert that to moles. So that's 12 times 6 plus 12, 16 times 6. 72 plus 12 is 84 plus 96, so 180 for 1 mole. That gives us half a mole of glucose solute. And then 900 grams of water. Divide that by 18 grams per mole for 1 mole. That gives us 15 moles of water. So that would mean it's 0.5 divided by 50.5. And that gives us X solvent. Actually, it says X solvent. So it's not 0.5, it's 50 moles of solvent divided by 50.5 total moles. That is equal to almost 0.9900900. And since that's X, so then P solvent is equal to 0.9900 times 23.8. That is equal to 23.56435. So it's equal to 23.56.
Okay. So are you done? What's your answer?
23.56 millimeters of mercury.
Right. We always have to give the units. Okay. So it sounded like you started by identifying the question. They're asking for the vapor pressure. Now the vapor pressure here, the only vapor is coming from the solvent. So that's P solvent. You've identified the correct formula. And the most important thing you did, I don't think we really did much warm-up for this, so it's good that you figured out how to do this. You saw that in order to find the mole fraction, you had to convert from grams to moles. We were told how many grams there were of each substance, but we need to figure out the fractions in moles. So it's good that you saw that you couldn't just figure out what fraction of grams comes from the water. You have to figure out what fraction of moles. And I think that basically you started using some of the stoichiometry techniques we went over in some previous sessions. So, for example, this is what I guess you did for the water. I don't know if you did this on paper, but you can use those same conversions that we did before to convert from grams to moles. And then you converted, I guess, the glucose from grams to moles too, and you got half a mole of glucose. So that's good because the molecular weight is 180 from here. And then you put in this. And it's good that you saw that we should not be putting in X solute. It's X solvent in this equation. All right, so that's good. I don't think I didn't really give you a warm-up problem for that. You figured out how to apply the formula, so that's good. Notice that now we're not using molality anymore. We're using a different measure of concentration. Also, this measure is not focused on the solute, but the solvent. So I think you ended up with the right answer here. One thing we haven't been doing that maybe we should be is trying to get a prediction. What's the one thing we could have predicted for this problem before we even got started? What's the one thing we could have predicted about the vapor pressure? Well, could we predict that the vapor pressure should be higher or lower than the pressure for pure water?
Well, yeah, we could have, but...
Yeah, so all I meant was, before we did this, should we have predicted that the vapor pressure of the solution would be higher or lower than the vapor pressure of the pure water?
Yeah.
Oh, sorry, I guess I didn't understand the question. Which one? Would we predict that the vapor pressure of the solution would be higher or that it would be lower than the pure?
Oh, it would be lower because you're adding a solute.
And this is vapor pressure lowering. So that would be a good thing to start getting in the habit of doing. And then our answer confirmed that. It did come out lower. Not that much lower, but a little bit lower. So that's the one prediction we could have made. We could predict that it's going to come out somewhat lower. All right, now suppose that they'd asked you a different question. Suppose they'd asked you, this.
What is the reduction in vapor pressure from adding?
What's the reduction in vapor pressure from adding the solute? How would you answer this question?
Well, it would just be the P naught 23.8 minus the 23.56, and that is equal to 0.24 millimeters of mercury.
Good. So I just wanted to point out this is a different type of question you might see on the test. Instead of asking you for the vapor pressure, for the level of the vapor pressure, they might ask you for the change in the vapor pressure. I don't think we really need to learn a new formula to see how to do that. So notice if they had asked you this question, you still would have solved it exactly the same way. Even if they ask you for the change in vapor pressure, the simplest thing to do is to start by finding the new level of the vapor pressure, since that's the formula that we've learned. And then you can simply do a subtraction to figure out the answer. So that's a different variant. We may as well just stick with this one formula because you could easily figure out the change from that formula. All right, good. Okay, let's try this.
The vapor pressure over pure water at 120 degrees Celsius is 1,480 million. What is the mole fraction of ethylene glycol? Must be present in the water to reduce the vapor pressure of water to 1 atm. 760. Well, you want to figure out mole fraction, so we're looking for capital X. And mole fraction of solute. X solute must be present in the water to so P of solvent is equal to X solvent times P naught of solvent. And you know P naught of water is 23.8 millimeters of mercury. And P solvent at 120 degrees is 1480 millimeters of mercury. That is equal to X solvent Then divide 1480 by 23.8.
Let's see. Let me interrupt you there. Let's see. What number? I'm sorry. Let me interrupt you. What number did you plug in here? Or maybe we should start. What number did you plug in here?
P solvent. 1480 millimeters of mercury.
And where did you get that from? Let me ask you this. What does this symbol stand for? What's the definition?
P naught?
Yeah. What is that? What's
the pure solvent. That is 23.8 millimeters of mercury.
Oh, it sounded like a second ago you plugged in 1480 for that.
No, I plugged it in on the left of the
okay,
equation.
Yeah, so let's take our time again. So what number did you plug in for this?
23.8.
Okay, yeah, and
millimeters of mercury.
And this stands for the vapor pressure of the pure solvent. It sounds like you got that 23.8 from the previous problem?
Yeah.
Okay, now that's fine because vapor pressure technically wouldn't change. However, there was important information that I didn't give you in the previous problem. What I should have said in the previous problem, vapor pressure of pure water is 23.8 at 25 degrees Celsius.
Oh,
I didn't actually specify that because 25 degrees Celsius is just normal room temperature. So that doesn't have to be specified. So the key thing is, I think maybe you're noticing now, vapor pressure changes when you change the temperature. After all, if you increase the temperature, do you think the substance is going to be more or less eager to vaporize? If you increase the temperature, would something be more or less eager to vaporize?
It's going to be more eager to vaporize.
Because it has more energy. Well, if it's more eager to vaporize, would it have a higher or lower vapor pressure?
It's going to have a lower vapor pressure.
We should actually review that for a second. That was something that we had some trouble with before. Remember that if something is eager to vaporize, it has a high vapor pressure. Because that means
that's right.
If it's eager to vaporize, that means that by the time it reaches equilibrium, there's going to be a lot of vapor, which showed that it was eager to vaporize in the first place. I guess we're having some trouble with these ideas. This would be a good thing to sit and think about for a while after the tutoring session. This is a little bit subtle. But if the vapor pressure is high, that must mean that liquid is eager to vaporize because it's going to end up with a lot of vapor at equilibrium. So let's try going through those thought steps again. If we increase the temperature, does it become more or less eager to vaporize? When we increase the temperature, are we more or less eager to vaporize?
We're more eager to vaporize.
So would the vapor pressure go up or down?
It'll go up.
Yes, because at equilibrium, we're going to end up with more vapor. And you can see that's matched by our numbers here. In the previous problem, I said that at 25 degrees Celsius room temperature, the vapor pressure of water is 23.8. But now here, notice that we have a really high temperature, and at this temperature, the vapor pressure is much higher. So the vapor pressure of water is a constant, but it's a constant that's different from different temperatures. So you can't just automatically use the number from the previous problem unless you're assuming that they're at the same temperature. Okay, this is part of the reason why boiling happens at a certain temperature. You have to raise the temperature high enough so that the vapor pressure equals atmospheric pressure. All right, so let's try again. I think there were some mistakes in the numbers we were plugging in here. What number should we plug in here for this symbol, for this problem?
1480.
Right. Because we have to use the vapor pressure of the pure solvent under these conditions. Now, what number are we going to plug in here? What does this symbol stand for?
It's the pressure at equilibrium.
Say that one more time.
It's the vapor pressure at equilibrium of a solvent.
That actually is incorrect, so let's think about that again. Remember that vapor pressure already refers to equilibrium. It's redundant to say at equilibrium. Vapor pressure already refers to equilibrium. The vapor pressure means what the pressure will be at equilibrium. The actual distinction between these is this is what the vapor pressure of the solvent is when it's pure, when there's no solute. And this is what the vapor pressure is when we've actually added the solute. So this is the actual vapor pressure now that we've added the solute. And this is what the vapor pressure would be if it was pure.
I see. So then we would actually put 760 there.
That's right. What we need there is this number, because this is the number we're going to achieve by adding the solute, 760. Why are you plugging in 760 and not 1 ATM? Because you want the units to match with these units over here. So the distinction between these is not about equilibrium, because what this means is if we add no solute at equilibrium, the pressure of the vapor would be 1480 torricelli. And this number means that when we add the solute at equilibrium, the pressure of the vapor will be 760. So both of these refer to vapor pressure, so they both refer to equilibrium. The difference is this refers to no solute, and this refers to when we have added the solute. I think I didn't quite take enough time to define those terms, so that's important to make a note of. Okay, so I think that was going wrong before is you were putting the 1480 on the wrong side of the equation. All right, so let's continue.
Okay, well, once we divide those two numbers, we get 0.513, and that is our mole fraction. And then it's asking what mole fraction of ethylene glycol must be present in the... Well, that's it. Once we divide those numbers, we do get the mole fraction, but that is the mole fraction of the solvent. I'm not sure if this number answers our question or not.
Okay, well, you're on the right track. You're on the right track. Well, does it answer the question or not?
No, it doesn't.
Okay. Well, take a few more seconds to see how you could answer the question.
What mole fraction of ethylene glycol must be present in the water to produce? Well, that's the mole fraction of the solvent. And since x can only be 1, and that's for a pure solvent, just subtract that from 1. And so then I guess it's minus 1. And that would be x of solute would equal 0.486. So x of the solute is equal to 0.486.
And what's the answer to the question?
0.486.
Okay. So the first thing we should have done on this problem is write down a symbol for what the question is asking. What would be a good symbol for what this question is asking?
Capital X solute.
That's right. Then you identified the correct equation to use to solve this. By the way, notice that when you take the test, there'll be some questions about boiling point elevation, some questions about freezing point depression, and some questions about vapor pressure lowering. So you have to decide which one you're dealing with. I think it's pretty clear this is about vapor pressure. Here's our equation. You solved this, and you saw that when you solved this equation, you got 0.5135. And then you did something that was very important. You realized that that doesn't answer the question. It's good that you realized that this didn't answer the question. It sounded like you were stuck. It sounded like you were giving up a little too fast. It sounded like you were asking for help. But when I told you to go back and work on it on your own, you actually figured it out. So that's good that you went back and figured this out. If we know that the mole fraction of the solvent, we can easily find the mole fraction of the solute by subtracting from 1. So you got the right answer. One thing I haven't mentioned is mole fraction has no units. Mole fraction has no units because it's just a fraction or a percent. This means that about 49% of the moles come from solute. So it's good that you figured out how to do that. So for example, all right, so I think we finished with this problem, and we tried to clarify then what these mean, and we noticed that vapor pressure depends on the temperature. So you can't always necessarily use the vapor pressure from the previous problem. So, what does this symbol stand for? In words, what does this tell us in words?
It is the vapor pressure, the actual vapor pressure with solute present.
Yes.
Of the solvent.
That's a good way to put it. This is the actual vapor pressure of the solvent with the solute present. The actual vapor pressure of the solvent with the solute present. We probably should have written that down before. So it would be good to write that down. What does this stand for?
It's the mole fraction of the solvent.
When the solute is present or not?
No.
So is this the mole fraction of the solvent in the pure solution or the mole fraction of the solvent when the solute is present?
Mole fraction of the solvent in a pure solution.
That answer actually didn't make sense. Because after all, in a pure solution, wouldn't the mole fraction of the solvent just be 1 all the time? In a pure solution, the mole fraction of the solvent would just be 1, right?
Oh, that's true.
Right. I think the reason you said that there was no solute is because you wanted to emphasize that this refers to the solvent. Well, it does refer to the solvent, but it refers to the amount of solvent when the solute is present. That's actually how you figured it out here. Well, not on this problem. So does this refer to the mole fraction of the solvent in the pure solution or when the solute is present?
When the solute is present?
Right. After all, the way that you would usually calculate this would be I haven't written this formula down before, but I think you pretty much figured it out on your own. This is the way to figure out what fraction of all the moles comes from the solvent. So notice we're certainly not ignoring the solute here. We're not ignoring the solute. That's part of the calculation. Notice that if there was no solute, this would just be 1. If this was 0, then this would just be 1. All right, and then what does this symbol stand for?
It's the vapor pressure of a pure substance with no solute present.
With no solute. So I should have been more careful when we started to define what each of these terms means. Also, if X solvent is 0.4, what would be X solute?
0.6.
That's just common sense, because the two mole fractions have to add up to 1. So that's something that you figured out for yourself on the previous problem. Okay. Let's see. Let's see here. This is going to work. Okay, so let's work on this. You can start working on this on your own, but if you get stuck, I'll give you some help. So think about how would you start working on this?
The solution has 10 grams of solute and 6 moles of solvent. The mole fraction of the solute is 0.03. What is the molar mass of the solute? Well, we know that X solute is equal to 0.03, and we are trying to figure out the molar mass, which is grams of solute per 1 mole of solute.
Are you working on that?
I'm having I'm not quite sure how to approach this one.
Okay, that's fine. I can give you some help. This is a little different from what we did before. You had some good steps at the start. One thing that you did that was good is that you processed this number. You took this 0.03 and you labeled it with the right symbol. That's an important step. Another good step you took is that you wrote down the units for what they're asking us. Now, it sounds like you might not have done the next step. Now, one thing you did is you said this was grams of solute per 1 mole of solute. But the problem is that in order to calculate this, we need to put a number on the top and the bottom, because we don't know, we know that the one here would just be hypothetical. This would tell us how many hypothetical grams you would have if you hypothetically had 1 mole of solute, but we don't actually know that we have 1 mole of solute. So instead, we should leave both the top and the bottom here blank. So let's see, where were we? I was saying that we need numbers for the top and the bottom of this fraction. Now, actually, one of these numbers we already know. What can we already plug into this fraction?
1 on the bottom.
Now, that was what I was actually mentioning a second ago. We don't know that we really have 1 mole of solute. So we can't plug in the number 1 here. What could we plug in on the top?
You can plug in 10 grams.
That's right. So you got off to a good start on this problem. You got off to a good start because you wrote down the units, but then it sounded like you didn't take the next step and plug in this number that we have, the 10 grams. Now you can see more clearly why we can't just plug in the number 1 down here, because we don't know whether there's really the 10 grams is 1 mole or not. You know, there's no real reason why the 10 grams has to be equivalent to 1 mole. We still don't know how many moles there are. So in fact, we're actually 50% done now. What's the last piece of information we need in order to solve the problem? What do we need to know now in order to calculate the molar mass? Since we know we actually have 10 grams of solute, what else do we need to know to calculate the molar mass?
The moles of solute.
Yeah, we need to calculate how many moles of solute we actually have. So we need to do that. This should remind you really of how we were doing these types of problems for freezing point depression and boiling point elevation. Now, the information that we have to figure that out is this mole fraction over here. Now, here also you got off to a good start. You got off to a good start by writing down this equation. The next step now, though, is to write the formula for mole solute. What would be a formula with variables for calculating mole solute? I'm sorry. What would be the formula with variables for calculating the mole fraction of solute? What's the formula with variables for calculating the mole fraction of solute?
P solvent is equal to X solvent times Oh no, well, we can't use that one.
That's right. We need an equation that's just the definition of how you would calculate mole fraction.
Mole fraction is moles of solute divided by moles of solvent plus moles of solute.
The mole fraction of solute is the moles of solute over the total moles. But notice the neat thing about that now is we've got an equation because we know that this is equal to 0.03. Remember, what was the last piece of information that we need to calculate to answer the problem?
We need to know the mole fraction of the solute.
Not quite. We already know the mole fraction of the solute. What we need to know is the number of moles of solute. But right. You see how we've made progress because now we have an equation. Now we have an equation about moles of solute. So let's work with this equation. What's the next thing that we can do that would help us with this equation?
So then what we can do is we can
what could we plug into this equation? The problem with this equation is that it has two variables. How could we get rid of one of the variables?
Oh, well, since 0.03 is on the top, it would also have to be in the bottom. So that would mean that we would just have 1 over moles of solvent then.
Let's see. That doesn't sound like that's coming out right. I think you might be still confusing mole fraction of solute with moles of solute. It sounded like you were going to plug in 0.03 on the top here. But this is the moles of solute, not the mole fraction. Those are two different things. We don't know how many moles of solute there are. Or maybe you just said that you could simplify by splitting this up. But we can't split this up into two equations. There's a little fraction math here. It sounds like you were maybe thinking of doing this. I don't know, is that what you were thinking? Anyway, this is not legal. This is not legal math. You can't just separate the denominator. What you could do, you could separate the numerator. Because you can see these have a common denominator, so they would add up like this. This is correct, but this is wrong. We can't just separate the denominator here. So we can't just split this fraction up. What's the variable that we need to get rid of in this equation?
We need to get rid of the mole of solute.
Actually, that we don't want to get rid of. That's what we want to solve for. We want to solve for the moles of solute, so we can plug it in here. What's the variable that we need to get rid of?
We need to get rid of the mole of solvent.
Right. I think you should go back and reread the problem. How can we use the information in the problem to get rid of one of the variables here?
Well, we can plug in 6 for the mole of solvent.
That's right. I think you might have been overthinking what the next step was here. We need to get rid of one of the variables, and we can do that by just plugging in a number, because we were given that number. So what would the new equation look like once you do that, once you plug that in?
So then it would be moles of solute over moles of solute plus 0.6 moles of solvent is equal to 0.03.
Say again, what number would you plug in here?
0.6.
Where did you get that 0.
I'm sorry, it's just 6.
Just 6, good. And over here?
0.3, 03, sorry.
0.03, or 0.03. Okay. Now what?
Now we would just multiply 6 by 0.03 and we'll get 0.18.
Okay, so what's the new equation?
Could you repeat that?
What we're trying to do is solve this equation for the number of moles of solute. So we need to keep rewriting the equation until we've solved it for moles of solute. What would be your next step for solving this equation for moles of solute?
We would just have to cross multiply.
That is the right step, yes. So go ahead and do that, and then tell me what's the next equation you get when you do that.
Then I get moles of solute is equal to 0.18 moles of solute. Actually, plus moles of solute
Like this?
Yeah.
Okay, I don't think that cross multiplication came out right. Let's do that more carefully. So if we're going to cross multiply, on the left-hand side, we'd have 1 times moles of solute. And on the right-hand side, we'd have 0.03 times moles of solute plus 6. Does that make sense so far? That's what happens when we cross multiply. So far, so good?
Yeah.
All right. Now we need to simplify this equation. So what does this equation simplify into?
So then we'll just we'll just distribute the 0.03, and then we'll get moles of solute is equal to 0.03 moles of solute plus 0.18.
Good. So I think originally when you were cross-multiplying, you were forgetting that we have to multiply the 0.03 times both of the terms down here. I think you were only multiplying it times the numerical value. So each step has to be done carefully on paper. It's really easy, as you can see, to make algebra mistakes as you're going through this. All right, and we're still not done. We still haven't finished, so what would be the next equation we could write down in our quest to simplify this equation?
Well, then we would have to subtract the moles of solute, so 0.03 moles of solute minus 1. So then that would be 0.07. Actually, no, 1 minus 0.03 is 0.97 moles of solute is equal to 0.18, and then divide by 0.18 moles of solute, and then we get 5.38 moles of solute.
What was that number again?
5.38.
What was the calculation you did?
0.97 divided by 0.18.
Did you write that out on paper? So what do we have to do algebraically to solve this equation?
Oh, we have to take, it's the opposite, 0.18 divided by 0.97.
Good, because algebraically, what do we have to do to solve this equation? What do we have to do to both sides?
We have to divide by 0.97 to get the moles of solute.
Right. It sounds like you might have done that step in your head instead of writing it down. The algebra here is a little tricky, so it's important to write every step down. It's important not to skip
0.185.
Let's see, yeah. On my calculator, it rounds out to 0.186. So we'll call that 0.186 moles of solute.
And since we know our moles of solute now, then we can just take 10 grams of solute and divided by 0.186.
Good. It's good that you didn't forget what our whole point was there.
I get 53.88 grams per mole.
Okay. Well, we better review that because there were a bunch of points there that gave us some trouble. So let's see. So by the way, now you can see why it would have been a mistake if we just plugged in 1 for the number of moles, right? Because there isn't 1 mole. There's 0.86 moles. Let's review some of the parts that gave us trouble here. So how would you interpret this 53.8? What does this 53.8 number tell us about the solute?
That's mass.
Actually, that's not quite right. It doesn't tell us that we actually have it doesn't tell us that we have a mass of 53.8. Remember, we actually have a mass of 10 grams. So try again. What does this number tell us?
We actually have that many moles in the solution.
I think that still's not quite coming out right. Because actually we know we don't have 53.8 moles. We actually have 0.186 moles, right? So try again. What does this number tell us about the solute? Try to use these units to interpret it. Remember, we always use the units to interpret. So using these units, what does this tell us about the solute?
There's 53.8 grams per 53.8 grams in 1 mole.
Right.
Of solution.
The way I would put that is, yeah, this is not about the solutions. The way I would put that is, if we hypothetically had 1 mole of the solute, it would have a mass of 53.8 grams. That's how we interpret molar mass. If we hypothetically had 1 mole of the solute, it would have a mass of 53.8 grams. Does that mean we really have 1 mole? Well, no. Actually, we know we actually have this many moles. And does that mean we actually have 53.8 grams? Well, no. We actually have this many grams. This is what I'm trying to do here is explain why it would have been a mistake to put the number 1 in at the beginning here. Remember that your first instinct was to put the number 1 here, and I can see why, because we often do put the number 1 on the bottom. But the problem with that is you were going to put the number 10 on the top. On the top of this fraction, we plugged in 10 grams of solute. Is this number 10 a hypothetical mass of solute or the actual mass of the solute?
It's the actual mass of solute.
It's the actual mass that we got up here. This was the actual mass. Therefore, we have to plug in, on the bottom to be consistent, we have to plug in the actual number of moles. That's why it was incorrect for you to try to plug in the number 1. Number 1 would be a legal hypothetical number of moles. Excuse me. But that would not be consistent with the number we're putting in on the top. If we're putting in the actual number on the top, we need to put in the actual number of moles on the bottom. That's what we had to do all this work to do, to figure out the actual number of moles. Now, how about over here? Here we have 53.8. Does this number 53.8 represent the, are we saying there's actually 53.8 grams, or is that a hypothetical mass?
That's a hypothetical mass.
That's the hypothetical mass you would have if you hypothetically had 1 mole. So this is the case where where we put the number 1 on the bottom. This hypothetical number 1 goes with the hypothetical mass. But if we're putting the actual mass on the top, we have to put the actual number of moles on the bottom. I guess that really is kind of a confusing idea, but well, hopefully with practice we can clarify that. All right, so we don't put the number 1 here. So what we actually had to do was, now you got the first step, which is that you wrote down this mole fraction. Then the next step is we need to get an equation for the number of moles of solute. Well, for that we just use the formula for the mole fraction. The mole fraction here is moles of solute over the total number of moles. And then I think we had a lot of algebra difficulties solving this, so that's important to review. First of all, remember that you can't split the denominator. You can't split this denominator. That's not algebraically legal. Instead, we have to cross multiply. And if you're going to cross multiply, it's better to write down every step so that you can see that you have to multiply the 0.03 times both of these terms, not just one. Then this step I think you figured out. You saw that what you had to do here is put the number 1 on the left-hand side, and then you subtract 0.03 from both sides, and 1 minus 0.03 is 0.97. Then I think we had another algebra issue of dividing by the wrong number. So the safest thing, again, is don't skip any steps. Write down each step, and then we plugged in. Okay, so this is an important type of calculation here. Let's keep going. All right, so let me ask you this. Oops. Okay, well, let's work through this problem.
Let's see, 15 grams, 5 moles of solute, or solvent. Mole fraction of solute is 0.05, so X of solute is equal to 0.05. What is the molar mass of the solute? Trying to figure out the molar mass, which is grams of solute over moles of solute. We have 15 grams, so we know that number. We're trying to figure out the moles, so mole fraction is equal to moles of solute divided by moles of solute plus moles of solvent, and that is equal to 0.05. And we know the moles of solvent, which is also 5, so we can cross multiply. And we get 1 mole of solute is equal to 0.05 times moles of solute plus 5 in parentheses, and then we distribute that 0.05, so we get 1 mole of solute is equal to 0.05 moles of solute plus 0.25. We subtract 1 minus 0.05 moles of solute, and we get 0.95 moles of solute, and that is equal to 0.25, so we divide by 0.95. So 0.25, divide that by 0.95, and moles of solute is equal to 0.26. My final answer is 50.07
Okay, great.
milligrams per mole.
I should have gone ahead and finished it. All right, so let's see. What did you plug into the top of this fraction?
15.
And on the bottom?
0.263.
Okay, and what did you say was the answer you got?
57.03.
I'll just call that 57. All right, now that's not a full answer without units. So what would be the units on your answer?
Oh, grams per mole.
Good. Grams of what per moles of what?
Grams of solute per 1 mole of solute.
So how would you interpret this number 57? What does this number 57 tell us about the solute?
For every 1 mole, there's 57 grams of solute. For every 1 mole of solute, there's 57 grams of solute.
Yeah, it tells us if we hypothetically had 1 mole of solute, which we don't, we would hypothetically have 57 grams of solute, which we don't. Okay, good. All right, so that seems like good progress. That went much more smoothly than the last question. So this is the method for doing this. Now, this is not quite a full problem like you might see on the test. This is just one piece that we'll need for the problem, but we can build on this. One thing I forgot to mention again is that something that I think was an issue in the last problem is don't confuse this and this. What does this symbol stand for?
That's mole fraction.
And this is?
Moles.
Yeah, it seemed to me like maybe on the last question there were some places where you were trying to plug in X for the number of moles. Maybe not, but anyway, that's something that we want to avoid. Let's see. Now, suppose they had asked you for the molecular weight of the solute. What would be the molecular weight?
57 AMU.
How would you interpret that? What does that tell us about the solute, that number 57?
That one single molecule of solute weighs 57 AMUs.
That's right. One molecule or one formula unit would weigh 57 AMUs. And another term they sometimes use is molecular mass. What units do you think you would use for that? I think so. That's what seems logical, because this seems to be the mass of a molecule again, not of a whole mole. So I think again that this should be 57 AMUs. One other thing I realized I wanted to talk to you about, but I forgot. Going back to this problem we did a little while ago, I forgot to mention this over here. So I just wanted to point out all of these colligative properties that we're going over don't work 100% in real life. They're all approximations or idealizations. all the formulas we're going over only work approximately in real life. But since you're taking an introductory class, all you need is the approximation. So anyway, how does it change the problem when it says I assume ideal behavior? Maybe you already realized it doesn't change it at all. We've been assuming ideal behavior all along. So whether they tell you to assume ideal behavior or not, you should still solve it using these same equations. But it's good to realize these do assume ideal behavior, which is never 100% correct. Something else I should have mentioned is we're assuming non-volatile solutes. Do you know what volatile means? Do you know what does it mean if something is volatile in chemistry?
It means it can evaporate.
Easily. That's good. That's good. So it has a technical meaning. It doesn't just mean that it's, I don't know, excitable or reactive. Volatile means easily evaporates. Something volatile has a high tendency to evaporate. So what does it mean if it's non-volatile? That means that it's not going to evaporate, or not much. So in all these problems, we're assuming that the solute is not going to evaporate. Of course, the solvent will evaporate because we're thinking about vapor pressure, but we're assuming a non-volatile solute. I should have said that too when we were talking about boiling point elevation and freezing point depression. All these colligative properties are assuming non-volatile solutes. I guess there are other approaches when the solute is volatile, but I don't think your class is going to cover that. So sometimes the problem might say the solute is non-volatile, but even if it doesn't say that, you're probably supposed to assume it. We're assuming that the solutes here are non-volatile. So if it says non-volatile solute, I'm just saying that doesn't mean anything's different. That's just the same thing we've been assuming all along.